Swayam Prabha. Digital India. Educated India.
Good morning. Welcome back to the next part of the lecture on post-processing concerns. So next concern is surface texture improvement. Surface texture or surface finish improvement. Additive manufacturing parts have common surface texture features that may need to be modified for aesthetic or performance reasons. The common surface textures are stray steps, power adhesion, fill patterns from extrusion or beam-based systems, witness marks from support material removal. So these need to be addressed. Staircase effect that I discussed, this is a fundamental issue in a layered manufacturing and it is difficult to overcome sometimes, although one can choose a thin layer thickness to minimize the error at the expense of build time. The thinner the layer is, the more is the time, but we will have a better finish in that case. But it is better to optimize the cost with respect to time and the quality. Next is powder adhesion. Powder adhesion is also fundamental characteristic of binder printing, powder bed fusion and powder based beam deposition processes. Powder has an adhesion and that also creates a texture specifically on the surface. Typical surface roughnesses which is taken from research are like these. For SLA, they showed the minimum layer thickness as 0.1 millimeter, roughness varied from 2 to 40 micrometers. And for selective laser sintering it was 0.125 and this was from 5 to 35. And for FDM it was the minimum layer thickness was 0.254 and surface roughness was 9 to 40 micrometers. For 3D printing, minimum thickness was 0.175 and the surface roughness was 12 to 27 micrometers. We can see that in these processes, the minimum thickness that is obtained here is in SLA and polyjetting processes, and the minimum surface roughness that is possible here is for SLA and polyjetting again. So this is a research way back in 2002. 15 years or 17 years later than this, there are certain materials which are developed and which can take the rapid manufacturing minimum layer thickness to 0.01 millimeter and the roughness that we can obtain is 0.2 micrometer. So this is the present status of the technology. The amount of powder adhesion can be controlled to some degree by changing the part orientation, powder morphology and thermal control technique. The type of post-processing utilized for surface texture improvements is dependent upon the desired surface finish outcome. If matte surface finish is desired, a simple bead blasting of surface can help even the surface texture, remove sharp corners from the stair stepping and give an overall matte appearance, that is for matte appearance. But if polish or glossy appearance is required, then the smooth and polished finish has to be got, then wet and dry sanding and hand polishing are to be performed. So it all depends to what extent do we need the surface finish. In many cases, it is desirable to paint the surface to improve the surface texture. For example, with the cyanoacrylate or a sealant prior to sanding or polishing. Painting the surface has the dual benefit of sealing the porosity by viscous forces, smoothing the stair step effect and thus making sanding and polishing easier and more effective. So this is the use of painting. Several automated techniques have been explored for surface texture improvement. Two of the most common utilized include the tumbling for external features, abrasive flow machining for primarily internal features. Abrasive flow is when internal features are to be finished, then abrasive flow machining can help to use abrasive to get the surface finish that is required. Tumbling, when external features is required, the material is kept into a tumbler and that is rotated and the powder improves the surface texture. So that is one of the ways. Next is accuracy improvements. There is a wide range of accuracy capabilities in additive manufacturing. Some processes are capable of sub-micron tolerances, whereas others have accuracies around 1 mm. Typically, larger the build volume and faster the build speed, the worse the accuracy for a particular process. So, bigger the volume and faster the speed and volume. If they are high, this implies accuracy is low. So, this is particularly noticeable for instance in beam deposition processes, where the slowest and the most accurate beam deposition processes have accuracies approaching a few microns, whereas the large bulk deposition machines have accuracies of several millimeters. So, these accuracies can also be seen here. The minimum layer thickness and surface roughness that is obtained. The minimum layer thickness implies the better surface roughness. Now, for accuracy improvements, we need to know what are the error sources. Process dependent errors affect the accuracy of XY plane differently from the Z axis accuracy. These errors come from positioning and indexing limitations of the specific machine architectures. For instance, are we using 2.5D machines, 2.5 axes or 3 axes or 4 axes, which kind of processing, which kind of stage are we using to get the rapid manufactured part. So, it all depends upon the orientation or on the indexing limitations of the specific machine stage or machine bed that is used. Then lack of closed loop process monitoring and control strategies, that can also lead to errors, and issues fundamental to volumetric rate of material addition such as melt pool or droplet size are the other factors. Future accuracy improvements in additive manufacturing will require fully automatic real-time control strategies to monitor and control the process, rather than the need to rely on expert operators as a feedback mechanism. Fully automatic and real-time accuracies, as we will discuss in rapid product development module of this course. Now, Internet of Things is also there. People can just order the product at their home and the product, the specific customized product, the shape, and that can be printed and delivered to them. So, those things are there. So, we need not to have an expert operators, the computers would work by itself and the product will be manufactured. So, there are certain interfaces which are developed for this. So, material dependent phenomena also plays a role in accuracy, including shrinkage and residual stress induced distortion. Now, integration of additive plus subtractive processes is one of the ways. We do some additive and then some subtractive processes. Now, this can be one of the ways to have better accuracy improvements. To recall, accuracy is the closeness to the original results. For instance, if I need this size as exactly 20 mm and I am exactly getting 20 mm, that is accurate. But there are certain tolerances. For instance, 20 mm is my final build I required, the diameter, and I am getting something like 20.2 or 19.8. So, this means it has 20 plus minus 0.2 and 0.2 tolerance. So, this is the closer to the final desired output, the higher is the accuracy. Generally, precision is there, but accuracy is not there. Precision is, for instance, if I am getting 19.7, 19.8, 19.7, 19.8, it is close to 19.75. So, this means the part is give us a precise reading which are close to 19.75, but there is always a difference of 0.2 to 0.3 mm in the negative direction. So, this is precision. So, accuracy, material dependent phenomena also play a role in accuracy, including shrinkage and residual stresses. Repeatable shrinkage and distortion can be compensated by scaling of the CAD model, However, predictive capabilities at present are not accurate enough to fully understand and compensate for variations in shrinkage and residual stresses. As in casting, we know there are certain allowances, shrinkage allowance, then we have draft allowance, those allowances are also to be put here. Quantitative understanding of the effects of the process parameters, build style, part orientation, support structures and other factors on the magnitude of shrinkage, residual stresses and distortion is necessary to enhance these predictive capabilities. For parts which require high degree of accuracy, extra material must be added. This extra material can be a thin layer throughout the part or the portions where we know that high shrinkage would happen. So, that extra material has to be added, that can be machined again, that can be machined off the major build. This extra material must be added, which is a critical feature, which is then removed via other subtractive means to get the desired accuracy. So, next after error sources we have model pre-processing as the way to accuracy improvement. Model pre-processing is for many additive manufacturing processes the position of the part within the build chamber and the orientation will influence the part accuracy, surface finish and build time. Thus, translation and rotation operations are applied to the original model to optimize the part position and orientation. So, shrinkage often occurs during additive manufacturing. Shrinkage also occurs during post-process furnace operations needed for indirect processing of metal or ceramic green parts. So, these need to be seen in the model pre-processing step only. The pre-process manipulation of the STL model will allow to scale a factor to be used to compensate the average shrinkage of the process. So, we are essentially talking here about CAE, computer aided engineering, where we see what would be the shrinkage, and when we need to compensate this shrinkage there would be always some features which will shrink slightly more or less than the average shrinkage. So, we need to see where the shrinkage is larger and on the other hand where the shrinkage is lower, and we need to work according to that. The specific factors can be taken, what scale factor or what extra material should be built accordingly. In order to compensate for shrinkage variation, if the highest shrinkage value is used, then ribs and similar features will always be at least as big as the desired geometry. So, this is important to have the segregated shrinkage factors. For instance, if there are ribs, like we say the bicycle wheel is there, bicycle wheel there are spokes. If we take the same shrinkage factor, the spokes are made very big. For instance, if I take this shrinkage allowance is 5 mm extra material. So, if the spoke size is 2 mm, an extra 5 mm diameter over that, that can make a spoke of 7 mm. So, the factors according to the size, for instance ribs and similar features should be determined, and that can be put separately to the parts which are being manufactured, to the portions of the part that is manufactured. However, channels and holes will be too large. Thus, simply using largest shrinkage value is not an acceptable solution. So, this is connected. Ribs and similar features will always be at least as big as the desired geometry, and channels and holes will be too large, right. So, thus simply using the largest shrinkage value is not an acceptable solution. In order to make sure that there is enough material left on the surface to be machined, adding a skin to the original model is also necessary. Adding a skin means there should be some material that is to be machined, that material has to be left everywhere. Many studies have shown that shrinkage variations are geometry dependent, even when using the same additive manufacturing or furnace process parameter settings. So, shrinkage allowance is similar to that in casting and in additive manufacturing. Next is machining strategy for accuracy improvement. Now, machining strategy is very important for finishing additive manufacturing parts, and tools considering both accuracy and machine efficiency, adaptive raster milling of the surface plus hole drilling and sharp edge contour machining can fulfill the needs of the most parts. Adaptive raster milling. When raster machining is used for milling operations, Step over distance between adjacent tool paths is very important parameter that controls the machining accuracy and surface quality. It is known that higher accuracy and surface quality require a smaller step over distance and vice versa. So, step over distance becomes an important parameter here. So, this is adaptive raster milling. Next is sharp edge contour machining. Sharp edges are often the intersection curves between features and surfaces. Normally, these edges define the critical dimensions. When using raster milling, the edges parallel to the milling direction can be missed, causing large errors. So, these need to be counted when a step over distance is used. So, this D is the step over distance. This D is step over distance and W is the slot width. Now, even when the CNC machine is perfectly aligned, the slot width error will be at least. So, this is slot width error, which is 2D minus delta 1 minus delta 2. Delta 2 is on the upper, delta 1 is on the upper side, delta 2 is on the lower side. So, this is W which is actually obtained. Here delta 1 and delta 2 represent the offset between the actual and desired location. When delta 1 and delta 2 become 0, this W error becomes 2D, which means that the possible maximum error for the slot using raster milling is approximately 2 times the step over distance. So, this we can use here. This is 2D minus 0 is equal to 2D. So, this is one of the models that determines the step over distance. Now, third machining strategy is hole drilling. Circular holes are common features in parts and tools. Using milling tools to create holes is inefficient and the circularity of the holes is poor. Therefore, a machining strategy of identifying and drilling holes is preferable. Most challenging aspect is to recognize holes in the STL file, as 3D geometry is represented by a collection of unordered triangular planar facets and thus feature information is lost. Now, people have used algorithms in recognitions of the hole just based upon because the hole and the surface have a closed loop here. So, these algorithms which are made up of sharp edges from the model, they are used to determine the holes. Now, the closed loops may not be necessarily the intersection curves between the holes on the surface. So, a series of hole checking rules are used to remove the loops that do not correspond to the drill holes. So, this is also one of the important machining strategy that needs to be covered. The intersection curve between the hole and the surface is typically a closed loop. By using this information, a hole recognition algorithm begins by identifying all closed loop made up with the sharp edges of the model. So, these are used by researchers to develop the algorithms and to develop the STL file only that has the hole drilling strategy in it. Next is aesthetic improvement. So, many times additive manufacturing parts are manufactured just for displaying in the showroom, or some marketing strategies, some marketing products are to be there. So, their aesthetic improvements is very important. So, highly aesthetic and appealing products are to be developed in additive manufacturing. For that, post processing options discussed in the above slides can be used. In some cases, a difference in surface structure between one region and other may be desired. This is often in the case of jewelry. So, the aesthetics of the parts is of the critical importance for its end applications. Often the desired aesthetic improvement is solely related to surface finish. So, in this case, finishing of the selected surfaces is only required. In cases where the color of the additive manufacturing part is not of sufficient quality, several methods can be used to improve the part aesthetics. Some types of parts can be effectively colored by simply dipping the part into dye of the appropriate color. So, this method is particularly effective for the parts created from powder beds, as inherent porosity in these parts lead to effective absorption. So, if painting is required, the part may need to be sealed prior to painting. Common automotive paints are quite effective in these instances. Another aesthetic enhancement which also strengthens the part and improves wear resistance is chrome plating. So, in this figure, a SLA part that is produced maybe using nylon, that is chrome plated, and after chrome plating several materials have been coated for additive manufacturing parts including nickel, copper and other coatings. In some cases these coatings are thick enough that in addition to aesthetic improvements, they also helped to get a robust enough to use as tools for injection molding or for EDM electrodes. Next is preparation for use as a pattern. This is also a post processing concern here. Sometimes the parts made using rapid manufacturing are intended to be used as patterns for investment casting, sand casting and other casting processes, and the other replication processes may be. So, then the use of additive manufacturing pattern for metal parts creation using a secondary molding or casting process is often the least expensive way to use additive manufacturing to produce a metal part, as many of the metal based additive manufacturing processes are still expensive to own and to operate. The accuracy and surface finish of an additive manufacturing pattern will directly influence the final part accuracy and surface finish. So, special care must be taken to make sure that the pattern has desired accuracy and surface finish in the final part. Also, the pattern must be scaled to compensate for any shrinkage that take place in the pattern replication steps. Because we are talking about patterns here, again shrinkage would come into play. There are certain patterns that needed to be prepared from the rapid manufactured part. Number one is investment casting patterns. In the case of investment casting, the additive manufacturing pattern will be consumed during processing. For this instance, residue left in the mold as the pattern is melted or burned out is undesirable. This is the example of investment casting patterns. Rings for investment casting made using this specific printer. Now, these are rings which are developed for investment casting. So, these are the patterns, those are used, these are patterns made, and these are the final rings. This is the final product and this is the pattern. This is additive manufacturing when the rings are made, additive manufacturing or rapid manufacturing. Next is the sand casting patterns. Both binder printing and powdered bed fusion processes can be used to directly create sand mold codes and cavities by using thermosetting binder to bind sand in the desired shape. One benefit of these direct approaches is that the complex geometry codes can be made that would be very difficult to fabricate using any other process. In order to prepare additive manufacturing sand casting patterns for casting, loose powder is removed and the pattern is heated to complete cross-linking of the thermoset binder and to remove moisture and gaseous byproducts. So, this is one of the sand casting patterns, that is for a cylinder head of V6 24-valve car engine. During loose powder removal and the right is the pattern prepared for the casting alongside a finished casting. So, this is the pattern, this is the casting that is obtained. So, this is loose powder and it is sand casting patterns which are prepared from rapid manufacturing. Property enhancement, the last post processing concern that we will discuss in this lecture. Property enhancement null thermal techniques. Powder based and extrusion based processes often create porous structures. In many cases, that porosity can be infiltrated by higher strength materials such as cyanoacrylate. Newer Proprietary methods and materials have also been developed to strengthen the various additive manufacturing parts. The normal thermal techniques, one of the best known technique is tempering, rapid prototyping tempering process. Rapid prototyping tempering is a collection of materials and treatment operations used to increase the strength, ductility, heat deflection and the other properties. This is rapid prototyping tempering. This is non-thermal technique. It helps to increase the strength, then ductility, then heat deflection, then flammability, resistance or resistance to flammability, and other such properties. So this actually induced the nanocomposite reinforcements that help to temper the material, and these properties are enhanced. This is non-thermal technique. Now the common post-processing operation for the photopolymer materials is curing. Okay, after tempering we have curing here. During processing, many photopolymerization processes do not achieve complete polymerization. As a result, these parts are pulled into a post-cure apparatus. That is a device that floods the part with ultraviolet and visible radiation in order to completely cure the surface and subsurface regions of the part. Additionally, the part can undergo a thermal cure in a low temperature oven, which can completely cure the photopolymer and in some cases greatly enhance the part's mechanical properties, that is curing. This is important. So there are certain thermal techniques as well. After additive manufacturing processing, many parts are thermally processed to enhance their properties. In the case of beam deposition and powder bed fusion techniques, for metals, this thermal processing is primarily heat treatment that is there to form the desired microstructures and to relieve the residual stresses. So heat treatment is an important post-processing technique that enhance the properties. That is, it develops the better microstructures which are specifically to the application that we need to apply. Then it also helps to relieve the residual stresses. So this heat treatment is more prominent in the case of metals. Like we know in general casting and machining processes where we machine or take off the material has some stresses developed in it. So we do certain heat treatments like annealing, normalizing, spherodizing. So those kinds of heat treatment can also be done here. So in the instances when traditional recipes for heat treatment developed for specific metal alloy being applied are commonly used. So traditional recipes, as I said, the common heat treatment processes are used. So in some cases, however, special heat treatment methods are also developed to retain fine grained microstructure within the rapid manufactured part while still providing stress relief and ductility enhancement. Before the advent of beam deposition and powdered bed fusion techniques capable of directly processing the metals and ceramics, many techniques were developed for creating metal and ceramic green parts using additive manufacturing. These were then furnace and post processed. So heat treatment is one of the processes. Now next is furnace and post processing to achieve dense and usable metal and ceramic parts. In order to prepare a green part for a surface processing, several preparatory steps are typically done. There are certain steps involved in this furnace post processing. We won't move into that direction, but yes, furnace post processing and heat treatment are the major thermal techniques which are there to enhance the properties of the additive manufactured or rapid manufactured parts. So with this we have discussed the major post processing concerns in rapid manufactured parts, which were support material removal, then machining, that is surface texture improvement, then we have the property enhancement. Certain people even say that metrological or inspection and testing is also the post-processing, the testing of the material, quality testing, inspection, all those things. Then to recapitulate, we see what are the various defects in rapid manufactured parts, how do we remove support material, then surface texture improvement concerns, then accuracy improvement concerns where we saw machining and other strategies, then aesthetic improvement where we saw surface texture improvement, then preparation of the parts to be used as a pattern, this we discussed. Then we saw the property enhancement using the non-thermal techniques and thermal techniques. So with this lecture is over. We'll meet again and discuss further on rapid manufacturing. Thank you.